We now move on to a fantastic presentation. So we're going quite granular into downstream, unlocking reservoir and refinery optimization through crude characterization. And this is from Ibrahim Atwah, PhD, Geology Technology Division for Saudi Aramco. So over to you, Ibrahim.
Hi, hello everyone. My name is Ibrahim Atwah. I'm the focus area champion of geofluids at the Geology Technology Division within Expec Arc in Saudi Aramco. And it gives me a great pleasure to present to you today my talk titled Unlocking Reservoir and Refinery Optimization through Advanced SARA-HPLC Crude Oil Characterization. So the outline for my presentation is as follows. This is the flow that I will walk you through today. I'll start by framing why crude characterization, especially SARA, still creates bottlenecks in both reservoir and refinery workflows. Then I'll introduce the micro SARA-HPLC system, what we changed, why it works, and how it removes many of the limitations found in traditional methods. I will show separation performance and with some results and few case examples that demonstrate how the method behave across different crude oil compositions. And I'll close with a broad impact, how this aligns with refinery optimization, digitization, and model-driven operations. Okay, so why crude characterization still limits optimization? SARA composition impacts critical upstream and downstream behaviors. On the upstream side, it governs flow assurance, asphaltene deposition risk, and fluid compatibility, in addition to predicting fluid types in the subsurface. And on the downstream side, the SARA distribution can influence fluid stability, fouling tendencies, and upgrading pathways. Despite this importance, crude characterization is still done with methods that are relatively slow, solvent intensive, and very operator dependent. This creates variability across labs, and that inconsistency makes it difficult to feed SARA data into digital models or to move it to rapid optimization cycles. This is the challenge that we want to solve with the micro HPLC system that we are introducing. Now, limitations of conventional SARA methods. There are several methods that are well established in the literature. Several decades of SARA method exists. Some of them utilize open column or thin layer chromatography, FID, and even earlier, and even also some HPLC systems. But they all share a recurring challenge, which is runtime is usually long, often either 1 hour or even more than 1 hour. And most of these workflows are manual and they require multi-steps. There is also the challenge of cross-contaminations between different fractions, such as the aromatics and resin. This is also well documented and can lead to misclassification of the SARA fraction. And most importantly, these methods are heavily operator dependent and results vary from lab to lab, making it really hard to use the SARA data confidently in models or for operational decisions. Because many steps rely on custom columns or complex configuration, standardization has been also difficult. This is what we wanted to address directly with the system that we are introducing, and I'll present about it today. Now, the micro SARA-HPLC workflow that we're introducing here, I'll walk you through what's new. What you see in the picture at the top is the actual system that we have built in our lab. Our goal was to design a system that anyone can deploy. There is no custom columns, no specialized hardware, and no off-lab modifications. The micro SARA-HPLC method utilizes a 3-column configuration that separates the SARA fractions in sequence. We also utilize a dual detection system. We have the ELSD detector for measuring the saturates, and the DAD detector to track the aromatics, resins, and asphaltenes. A key improvement is the micro volume injection in our system, and hence the micro SARA-HPLC. We use about 1.5 to 3 microliters of crude oil injection. This small volume needed help us avoid column overload, and also reduce the solvent use and maintain sharp fraction boundaries between the SARA classes. The full cycle of the analysis from injection to the column regeneration finishes in about 35 minutes, which makes this method practical for operational workflows. And because of the hardware is fully commercial, the method is reproducible and transferable between different labs. Now, I'll walk you through some separation performance and the elution windows of our analysis. One of the strengths of the micro SARA-HPLC is the clarity of the separation. Each of the SARA fractions elute in a well-defined window with minimal overlap between the different fractions. This eliminates one of the biggest issues in traditional SARA workflows, which is cross-contamination, either between the saturates aromatics or between the aromatics and the resins. The method doesn't require any deasphaltening step, so direct injection to the system is available. And this, again, improves the analysis time frame that's needed and reduce any inconsistencies in the analysis. The microvolume injection is key because it prevents the column from overload and maintains sharp fraction boundaries between the different fractions. Again, we tested this on crude oil from different compositions, from heavy all the way to light, with API gravities ranging from 10 all the way to 50. And we also examined this on rock extract bitumen. And with all of these different sample types, we consistently observed a clean, sharp separation of the SARA profiles, which is, again, essential for reproducibility and downstream analytics. Now, what you see on the right side is the HPLC chromatograms, which shows in green the saturate fraction, which elute first at about 2 minutes. Following that, the aromatic fraction, which elutes at about 5 minutes. And then the resin, and you see it in also blue, and it elutes halfway through the run. And lastly, the asphaltenes in red elutes at about 25 minutes. And after the asphaltene, we see a small peak. And this is the column regeneration peak. And so the entire run finishes in about 35 minutes, which is a break record in the SARA analysis time. Now, moving to method validation, what we have done after we developed this micro HPLC system, we wanted to make sure that there is no cross-contamination between the fraction. So a critical part of developing this method was verifying that each fraction is pure and correctly assigned. We validated purity using GCMS and FTICRMS. Both techniques confirmed that each collected fraction of the saturates and aromatics, as confirmed by the GCMS, that they are pure and there is no cross-contamination. Similar thing with the FTICRMS for the resin and asphaltenes, confirmed that we contain the expected molecular families with minimal cross-contamination. The calibration curves allowed excellent linearity, showed excellent linearity with R square values reaching 0.99 across the different concentration ranges. For reproducibility, we used a reference Norwegian or crude oil, and it's abbreviated as NSO1 for reference. And the method showed less than 1% deviation across multiple runs over a 7 months period, which is better than most conventional SARA workflows. Most importantly, results are consistent across different crude types, and the values align well with the ranges reported in the literature of the same classes of oils. Again, this gave us really high confidence in the reproducibility of our method that we are introducing. Now, moving to method validation and the reproducibility, what you see also here is a bar chart of the different sample types or crude oil types that we looked at, and the rock extract as well. And it shows the run in 4 times, and basically it captures, and what you see in blue is the saturates, in green is the aromatics, and resin is in the yellow color, and red we have the asphaltenes. And what we're trying to convey here is the standard deviation and the variability within the 4 runs of each samples. Again, reproducibility was less than 1% for each fraction, which is again a break record in the SARA analysis method. This gave us high confidence in the method that we're developing and the stability of the detectors of giving the same response of each fraction. Now, moving on to the impact of this workflow for refinery, and especially also what we talk about here in this event for digital workflows. With such standardized method and very reproducible, digitization of such method becomes very critical and can open windows to so many other improvements that can be achieved. A critical part of developing this method was verifying that each fraction is pure and correctly assigned. And one of the biggest advantage of this method is how directly it feeds into operational decision making. Be it, very reproducible and anyone can build it, as well as being it very quick. You get the results within 35 minutes. The high fidelity SARA data allow refineries to make better crude selection and blending choices, especially when evaluating new feeds or spot cargoes. Because the heavy fractions are accurately resolved, we can quickly flag stability and fouling risk ahead of time. Something that directly impacts heat, for example, heat exchanger performance and unit availability. The short turnaround time means that instead of waiting for days for the SARA data to come back, the SARA data can now support daily and even real-time model updates. This is especially valuable for, if we want to talk about what can be potentially done from out of this, instead, such as digital twins, planning models, and machine learning workflows that need consistent input and reproducible data across different labs. Because of this method is reproducible across labs, it becomes possible to standardize the SARA measurements across plants and build reliable benchmarking datasets. Now, this brings me to the conclusion and future outlook of such approach. The micro-SARA HPLC provide a practical step forward for crude oil characterization, be it in upstream, when evaluating fluids in the subsurface, near the well, or in the refinery after processing the crude. It overcomes the major limitation in speed, reproducibility, and fraction purity that have historically held back operational use of SARA data. The method supports optimization workflows across upstream, midstream, and downstream settings, and is ready for integration into digital tools, whether planning models, AI-driven blend optimization, or digital twins. Looking ahead, we're expanding our crude oil libraries, especially for our operation down in the subsurface, to develop broader SARA benchmarks. In our case, we're trying to build these libraries to predict the crude oil origin or crude oil type. We're also working on the resin subtractions for deep chemical insights and evaluating how microsara pattern could correlate in the downstream cases for refinery performance and indicators like fouling and stability. At this, as this progresses, again with a standardized SARA system, multi-lab validation will help define a reproducible industry standard for SARA analysis. With this, I end my talk, but I'd like to highlight a few things before I open it for Q&A. This work has been published in ACS Omega, and it's available to download online. You can scan the barcode. We have all of the method details, all of the system model and the method parameters available online. It's available in PDF, so you can scan the barcode and read more about the approach. With this, I thank you for your attention, and I will open the floor for any Q&A. Thank you so much.
Thank you, Ibrahim. It's always good to get a real focused presentation in an event like this, because obviously we talk a lot about different aspects of downstream, but I think it's really good to have a sort of a focused on crude and reservoir technology. So thank you very much for that. Unfortunately, we didn't have time for any Q&A because we had to work with what we had on this one, but it was a brilliant presentation. However, if you wish to get in contact with Ibrahim, please get his details from us and also from the agenda as well. So thank you, Ibrahim, for your brilliant presentation. We're now on to a quick break, 10 minutes. We'll be back.